This lecture is part of a series on algebraic topology and will be about the fundamental group of a knot. So if we look at a couple of knots, for example, we might have the trivial knot, just consisting of a loop that's not knotted at all, or we might have, for example, a trefoil knot looking like this. And it's kind of intuitively obvious that these two knots are different, but it's a little bit trickier to actually prove it mathematically. Well, why would you want to bother proving something that obvious mathematically? Well, sometimes it's not obvious. For instance, if we look at a table of knots, this is from Rolfson's classic book on knots and links. So he's got some pictures of knots in the end, and if you look at this page here, you see there's an example of 10 knots, and two of these knots are actually the same. And I think you'll agree it's not at all obvious which two are the same. In fact, this is a rather notorious error in tables of knots. A guy called Perko noticed a few years ago that many of the standard tables of knots listed two knots as being different when they were the same. Anyway, we would like a systematic way to tell whether knots are the same or not, and one very easy one is to work out the fundamental group of the knot. Strictly speaking, this really means the fundamental group of the knot complement. I mean, the knot itself is just S1 with fundamental group Z. And last lecture we worked out the fundamental group of a circle, and its pi1 was just the integers. So we now want to figure out how to find the fundamental group of a more complicated knot like this. So how do we calculate it? Well, we're going to do it in a couple of steps. First of all, we replace the complement by a certain deformation retract. That means you sort of squish the complement onto a smaller space, and then we're going to calculate the fundamental group of the deformation retract, which will be a bit easier. Before doing this, just remark there's a useful method for calculating fundamental groups. So I've got a space X, and I want to take a copy of the unit disk, a two-dimensional ball, and I'm going to join it to X by choosing a loop in X and gluing this loop to the boundary of this ball here. So I'm sort of adding a 2 cell to X by gluing the boundary to it, and we can ask, what is the fundamental group of this? Well, what we have here is we have a copy of X, and then we have a copy of B2 here, and their intersection is going to be a copy of S1. And we can use Van Kampen's theorem to work out the fundamental group of this. So the fundamental group of X together with the 2 ball is going to be the fundamental group of X, and then we take the amalgamated product over the fundamental group of B1 over the fundamental group of a circle. Well, that's easy to figure out because the fundamental group of B1 is just a trivial group, and the fundamental group of a circle is just Z. So what we're doing is we're taking a Z inside pi1 of X and making it trivial. In other words, we're not quite quotienting out pi1x by the subgroup Z, because this need not be a normal subgroup, but we're quotienting it out by the normal subgroup generated by a particular element. And the particular element is just the boundary of the B1 in X. So attaching 2 cells to a space is a sort of method of killing off elements of the fundamental group. So now let's try and figure out a good deformation retract of a knot. So we can think of the knot as lying, we can sort of project it to a plane. So we can think of this knot as lying in a plane, except there are a few points where it's not quite a plane. What we do is we think of the knot as being a sort of train track. And the train track has a few points where there's a sort of bridge like this. So we can think of the we can think of that there's a train track which is mostly in the plane, except every now and then there's just a little bridge where the train track has to go over itself. And what we're going to do is we're going to form a deformation retract. So the first step is we just take the plane that the knot is lying on, except we push the plane slightly below the knot, so the knot is slightly above the plane. And step 2 is we're going to add tunnels, or we're sort of going to build tunnels. And the way we do this is as follows. Suppose we've got a bit of train track. It might go sort of like this. Maybe it goes like that. So what we do is we first of all forget about all the bridges, and if we sort of demolish all the bridges, we've got several pieces of track, and above each piece of track we're sort of going to build a covering so that the track sort of ends up being in a sort of tunnel. So here we build a tunnel for this piece, and we're going to build a tunnel for this piece and a tunnel for this piece, and so on. And let's think what that does to the pi1. Well, the pi1 of a plane is just trivial, of course. And now let's think about what happens when we add a tunnel. Well, if you sort of squish the tunnel up, you see we're really just adding a loop to the plane by taking a unit interval and joining its two ends to the plane. So pi1 of the plane plus these tunnels is just a free group on n generators, where n is the number of pieces of track we get if we demolish all these bridges. Well, we still haven't got a deformation retract of our knot, so let's take a little closer look at these bridges. So what happens is each bridge is going to look something like this. So here we've got a bridge, and here we've got something going under the bridge, and we've got several pieces of tunnel. So we've got a piece of tunnel covering this, and this piece of tunnel actually goes under the bridge. And then we've also got a piece of tunnel covering this bit joining one end of the bridge, and another piece of tunnel joining the bit going over the other end of the bridge. Actually, I really wanted to go all the way up to there. And now what we're going to do is we're going to cover the bridge with a little covering. So what I'm going to do is I'm going to cover the bridge with a green bit. And if you think about it a bit, you can see that all these tunnels, together with all these green bits covering the bridge and the plane we started with, is actually a deformation retract of the complement of the knot, because you can sort of push everything above this construction downwards until it reaches the construction. You can push everything below the plane upwards, and then you can take everything inside one of these tunnels and push it away from the knot until it hits the boundary of the tunnel, or maybe this bridge. So this thing consisting of the plane plus all these tunnels plus these green coverings of the bridge is actually a deformation retract of the complement, so it has the same fundamental group. Well, now we want to work out what is the effect of adding these bits covering the bridge. Well, let's take a look at the green bit. So here we've got a sort of green bit, which is really a 2 ball, and we're sticking it on. And if you look, this end gets mapped to a bit of one of the tunnels. So if the thing going round this tunnel is called xj, and this tunnel is called xi, and round this tunnel is called xk, then you see this bit is just xj, and this bit here is xi, or maybe xi to the minus 1, and this bit here is xi to the minus 1, or maybe xi, and this bit here is going to be xk. So you remember adding a ball kills off the boundary. So what we get is we sort of have this extra relation xi, xj, xi to the minus 1, xk, to the minus 1, sorry, it should be minus 1, is equal to 1. In other words, xi, xj, xi to the minus 1 equals xk. So this gives us the fundamental group of the complement of a knot. We have a generator for each of these bits of track when we remove the bridges, and we have to add an extra generator for each bridge which says something is the conjugate of something else. It's a little bit easier instead of if we've got a knot here. So I was talking that we have a generator for the bits you get by removing the bridge. So we'd have a generator for this bit, and this bit. Well, that's a bit confusing. It's really a little bit easier if you turn the knot upside down, and then you see that what is happening is you get a generator for each component of the knot. And so not for each component of the knot. I mean, if you draw the knot in the plane and draw these gaps, we get a generator for each of these lines where I've put little gaps where the line is passing under something else. And for each of these crossings, we get a relation between the generators, and it's a little bit tricky getting getting the signs of these crossings right. You remember I was saying we have a relation xi, xj, xi to minus 1 equals xk, and it's a bit difficult remembering whether this should be an xj or the inverse of xj and so on. It's actually useful to sort of orient the knot by putting arrows on it in order that you can tell whether you should have a, sometimes maybe you should have a minus sign there and an xj there, depending on how everything is oriented. I'm not actually going to give exact details of whether you should use an element or an inverse, because if I try and do that, I will undoubtedly get it wrong half the time, and people write all sorts of rude comments pointing out my mistakes. I'm just going to cheat by not actually giving the details. Instead, let's do some examples. Let's try it with the trefoil knot. So here we've got this trefoil knot, and you see there are 3 components. So the generators corresponding to these, let's call them x1, x2, and x3. And then if you write down the presentation for the group, it's got generators are going to be these loops x1, x2, x3. That means you're taking a loop that sort of goes round this bit x1 and then comes back. And the relations are going to look somewhere x1, x2, x1 to the minus 1 equals x3. So that would be the relation you get from this crossing here. And then we get a relation x2, x3, x2 to the minus 1 equals x1, and x3, x1, x3 to the minus 1 equals x2. So we've got a group with 3 generators and 3 relations. And we want to know that this is different from the fundamental group of the trivial knot, which is Z. So how do we tell that? Well, one easy way to simplify a group would be to take its abelianization. So you notice this group is non-abelian, which is a bit tricky. So let's abelianize it and see what we get. Well, if it's abelian, this says that x2 is equal to x3 because it's conjugate to it by x1 and so on. So we get x2 equals x3 equals x1. So its abelianization is just the integers because all the generators become equal, and you see this doesn't actually distinguish the trefoil knot from the unknot. In fact, if you think about it a bit, you'll see that if we take the fundamental group of any knot and abelianize it, then we always get the integers, because the knot relations say that whenever we've got a crossing, the generator corresponding to this bit is conjugate to the generator corresponding to that bit, conjugate by the generator corresponding to this bit. And therefore, since the knot is connected, all the generators are conjugate to each other. So if we abelianize it, we just get the integers. So we have to think of something a little bit cleverer to do than just abelianizing the knot. And what we can do is we can look at homomorphisms from pi1 of the knot to a small group. And the small group I'm going to take is going to be the smallest non-abelian group, which is the symmetric group on 3 points. And you remember this is 3 generators, 1, 2, 2, 3, and 3, 1. And now I can take a homomorphism from pi1 of the trefoil to this group by taking x1 to 2, 3, x2 to 3, 1, and x3 to 1, 2. You remember these are just the permutations that swap 2 points. And if we have a relation x1, x2, x1 to minus 1 equals x3, you can check this relation holds for these 3 generators, that this element conjugates that one to that one. So we do indeed have a homomorphism from pi1 onto the symmetric group on 3 points. And this implies that pi1 of the trefoil is non-abelian because it's got a map onto a non-abelian group, so it can't possibly be an abelian group. And this is enough to show that pi1 of the trefoil is different from pi1 of the trivial knot, and therefore the trefoil knot really is a knot. Let's do another example. So we've shown the trefoil is not a trivial knot. Now let's look at the following links. So first of all, we've got a link here, and then we've got this link here. So here we've got 2 circles that are linked and 2 circles that are not linked, and we want to prove mathematically that these are different. In other words, these things really are linked. Well, what we can do is we can just calculate pi1 of the complement. And here we've got links rather than knots, but that doesn't really make a whole lot of difference. And if we calculate the fundamental group of this, we find we've got 2 generators, x1 and x2, and no relation. So we get the free group on 2 generators. Notice, by the way, that the abelianization of this is not z, but z squared. The proof that the abelianization of a knot is z uses the fact that the knot is connected, and here a link obviously isn't connected. Now let's try and work out pi1 of the complement of this. Here we've got 2 generators, x1 and x2, and the relations say that x1, x2, x1 to minus 1 equals x2, and x2, x1, x2 to the minus 1 equals x1. So these are relations coming from these 2 crossings. So this just says that x1 and x2 commute. So here the fundamental group of the complement is the free abelian group on 2 generators. It's a little bit funny because this looks more complicated than just having 2 disjoint circles, but the fundamental group of the complement actually turns out to be simpler. Anyway, so this one, the complement has an abelian group as its fundamental group, and here the group is non-abelian. Therefore, these 2 circles really are linked, that they are different from 2 unlinked circles. There's a sort of amusing trick you can do with this. What we can do is we can take a couple of circles, and I'm going to draw these circles in blue, and I'm going to take 2 unlinked circles, so I'm going to have them like this, and I can draw a sort of loop going round them like this. We've got this right. So there. Now, I think you can, it's sort of intuitively obvious that this pink loop can't be taken off these 2 blue circles. Well, now suppose I take these two blue circles and I kind of join them together. So I'm going to take exactly the same picture as before, except I'm going to move these two blue circles so that they are linked with each other like this. So otherwise I'm going to take the pink loop doing the same thing. So let me try and get it right. And here, so I've taken this link and I've made it even more complicated by linking these two blue circles together. And the amazing thing is you can now pull this pink loop off these two blue circles. And I think I'll use two carabiners to be the blue loops, and I'm going to use this loop here to be the pink loop, and I'm going to try and arrange this so that it copies the loops here, and this is really quite tricky to get right. I get it wrong about half the time, so that goes around like that. And now this yellow loop is firmly attached to these, and I'm going to try and make these two carabiners link each other as in that diagram, so they sort of link like that. And now, if I'm lucky, I can now take the yellow loop off, and half the time it works and half the time it doesn't. So if I put it like this, it actually comes off. Okay, that has actually worked for once. Next lecture I'll be probably talking a little bit about the Alexander horn sphere and how to work out the fundamental group of its complement.